Okay, good evening, everybody, and welcome to AREG's March meeting. My name's Jared, VK5ZQV. I'm the president of AREG. This evening, we have David, VK5DGR. Yeah, right, David, who's going to talk about RADE. And so welcome, everybody, and I'll hand it across to David. Thank you very much, David.
Thank you. Do we have the slides up? Good. All right. Yeah, hi, my name's David, Victor Kilo 5 Delta Golf Romeo. Tonight I'd like to talk about RADE, which is all about machine learning for speech over HF radio. And I'd just like to acknowledge this work was done by a team of people from freetv.org, and it's been supported by a grant from Amateur Radio Digital Communications, otherwise known as the ARDC. Okay, so just a bit of an outline. First, I'd like to introduce the mode, what it's all about. Then talk a little bit about a paradigm shift in designing radio signal processing in terms of the design versus training shift that you get with machine learning. Then we'll have a bit of an overview of RADE, the mode, and a little bit how it differs from conventional signal processing and digital voice modes, and then a bit of a conclusion with some links. Okay, so RADE stands for Radio AutoEncoder. An autoencoder is a machine language design that we've employed for this application. So what we've done here is applied machine learning to the problem of sending speech over HF radio. The mode combines some traditional DSP with some more modern machine learning to encode and decode speech. The way you can use it is you have a PC running an application that connects to your SSB radio by a couple of sound cards. Why you might want to run it is that it delivers 8 kilohertz audio bandwidth over HF radio, quite high quality speech. It works at high and low SNRs and can handle some of the problems that HF throws at us, like multipath fading. Okay, so I'll start off with a few examples. Hopefully these should play okay. So these are just from some blog posts on the FreeTV website for some development we did last year. This is a sample of submitted to us by Rick, W7YC, of his colleague Joey, transmitting over a path from Texas into New South Wales. So down the bottom, we don't have this screen up. Hang on, we'll get it across. There we go. Now that's a spectrogram there of the signal. What we sent first was a tone to calibrate and measure SNR. Then that's the SSB. And then we sent the RADE signal there. This was a long distance path, quite deep fade in the middle of it. That's present on both the RADE and SSB, but a bit more obvious on the RADE segment there. This is like a waterfall on its side, so time moves from left to right. So hopefully we can hear the SSB first.
Seashells down by the seashore.
K5CJ testing 1, 2, 3 AutoEncoder. She sells seashells down by the seashore. Testing 1, 2, 3, 4, 5 K5CJ.
So the SSB again. Anyway, you sort of get the idea there. That was at around 4 dB SNR, 25 watts. You can notice the RADE signal does fall over in the middle of it, but it recovers fairly gracefully and you don't lose too much of the speech. I'll do that again.
K5CJ testing 1, 2, 3 AutoEncoder. She
Might have detected a bit of a stumble there as it went through the deep fade. It's not magic, can't get through when there's no signal there. And there was another sample. This is me a bit earlier on. I was transmitting a signal from Adelaide here across to some SDRs in Western Australia. So this one's over a couple of thousand kilometres. And I wound the power down a bit so I could sort of give it a hard time. This is about 0.5 dB peak signal to noise ratio on a couple of watts. Once again, there's this sort of calibration tone that lets us measure the SNR of the channel. The SSB's in here somewhere, and this is the RADE. And in this case, you've got this heavy frequency selective fading, this sort of barber pole effect. And they're both at the same peak power level, driven by the same radio. So the SSB.
CQ. This is VK5 Delta Golf Romeo, Victor Kilo 5 Delta Golf Romeo, calling CQ for UV 2020.
So doing a reasonable job there too, over a fairly heavy multipath faded channel. A little bit later on, the same day, I wound the power up and did a higher SNR sample just to see what the difference was. So this is the SSB.
CQ. This is VK5 Delta Golf Romeo, Victor Kilo 5 Delta Golf Romeo, calling CQ for UV 2020.
So now the SSB is a lot easier to understand. Some of you might have picked up it's fairly heavily compressed. We wanted to sort of do the best job we could, but still quite a lot of background noise despite the fairly high peak SNR of around 80 dB.
CQ. This is VK5 Delta Golf Romeo, Victor Kilo 5 Delta Golf Romeo, calling CQ for UV 2020.
So that actually doesn't sound a lot better than the 0.5 dB sample. So it doesn't, it does a fairly good job, but once you've got rid of that noise, well, that's sort of good as it gets. Okay. Let's see if we can get back to the PDF. There we go. Okay, so that was the examples. RADE's an outcome of the FreeDV project. For about 15 years, a bunch of hams have been working on this problem of open source HF digital voice for amateur radio. Fortunately, about 2 years ago, we were awarded an ARDC grant that has allowed us to push things forward quite significantly. It's managed by a 6-person project leadership team. That's kind of a requirement of having these grants. You need to have a fairly formal structure in place. And we have something called a financial sponsor, which is the Software Freedom Conservancy, which deal with a lot of other open source projects as well. They provide the legal framework we needed to receive the grant. One of the project goals is a voice mode that's competitive with SSB at high and low SNRs. Okay, so I'd like to talk a little bit about what makes machine learning different from the regular signal processing that we've all been doing until now. Previously, say we wanted to design something like a radio, we'd figure out all the signal processing steps. So you might say, I need a mixer, I need a filter, I need a low-pass filter. And you'd put them together block by block to make the thing that you're making. However, with machine learning, the emphasis is on training a neural network. You start with a neural network. This is some sort of blank slate, and then you work out a way to train that to do what you want to do. So I just wanted to illustrate that with an example of based on a simple AM receiver, something like a crystal set. And I'll show you how we can build the detector block there using machine learning. So this simple radio, you have input RF, which might be from your antenna, some sort of bandpass filter, which is a tuned circuit perhaps. Then there's the detector that demodulates the AM radio, and that's typically something like a diode. And then we have a low-pass filter, and you get your output speech. So very simple sort of radio receiver. So what we're going to try and do now is design that diode detector block using machine learning. So the way we do that is we start with an untrained neural network. We then collect some training material, and that's examples of what we put in the input of this network and what we'd like to see ideally at the output of this network. Then what we do is we start running these samples through the neural network. So in this case, the neural network's in that ML detector, machine learning detector. That's our blank neural network that we start with. We then take the samples from the AM. We see what comes out of the detector, which is that ML detector output block out of the blank detector over here. And we compare that to the ideal. What would an ideal detector give us? Once we've compared it, we then adjust the machine learning detector. The neural network, we adjust that to get a little bit closer. And that process repeats itself over many thousands of samples. And eventually you hopefully train the network to look something like, in this case, a machine learning detector. So this is, I wrote a little Python program that does just this. The top plot is the AM in. At the bottom is the ideal detector output, which is really just half-wave rectified version of what's on top. Now at the bottom, over time, that's the output of the neural network. And as you can see, it starts off, it's a bit rough. It looks a bit like the input signal, but eventually towards the end, after about 1,000 samples, we've got something that looks like the ideal detector output. So we've trained a neural network to be a AM detector or a diode, basically. I just generated the sample signals directly in software. Yeah, a sampled version of an analog signal. Yeah. Okay, so we designed a detector using machine learning. Big deal. We could have just put a diode in there. That's a lot easier, and we know it works pretty well. But here's the problem. Sometimes we don't know the best way to design a complex system. We have a bit of a guess, but it's an approximation. This is particularly true with real-world signals like speech, for example. Every time we try to compress speech, it's really just a model that we put together, and it's not perfect. So a lot of real-world problems are complex, and perfect designs don't exist. We can't just put all the block diagrams down and expect them to work. But often we have a really good idea of what success looks like, or in the case of audio systems, what success sounds like. We can quantify that. So the idea of a lot of this machine learning work is we just treat the system, the neural network, as a black box, and then show it examples of what we would like to see and train it. Now, the benefits of this is that machine learning has provided some real step changes in the performance for many applications. Big increases in performance over what we could previously do a few years ago with classical signal processing. And this includes speech synthesis and compression, which is what we're interested in for digital speech over HF. So about 18 months ago, a colleague of mine, John Mark, was doing some work compressing speech for internet applications. Now, the internet's an interesting channel in that you either get a packet of voice go through the internet or you don't. If it does go through, it's generally perfect. You know, the checksum passes. And if the packet gets lost on the internet, you don't get it at all. That's a little bit different to a radio channel where you might put a signal through it, but it gets corrupted by noise. So John Mark wondered, could these same techniques that he was using and his team for compressing speech over the internet be applied to noisy signals over radio channels? In a pretty short amount of time, we had a chat about this. He developed a quick proof of concept, and then myself and the team I've been working with spent most of last year wrapping a modem around it and turning that into a practical HF voice system. We employed, we worked with a bunch of hams around the world who kindly helped us to crowdsource the system. They do things like take their own voice, record it, send it over there, encode it using the RADE system and send it over to SDRs around the world, and we compare it and develop it that way. So we had a lot of help with kind help from hams around the world to develop this. My colleague Munir then integrated the final thing into the FreeDV GUI application to give us all a PC-based application that we could all run, hook up to our radios and run RADE in real time. So now to talk about RADE proper, we've talked about a bit of how machine learning trains things and how it differs from classical signal processing. So I'd like to step back and talk about a classical digital voiceover radio system. Now this could be something like an existing FreeDV mode, or if anyone's got a DMR or P25 handset, this is what's going on inside your handset. We start with some input speech, There's something called feature extraction, where we do things like DFTs and various algorithms to extract information about that voice signal. It could be like the spectrum, like a waterfall, for example, or the pitch of the voice. They're kind of floating point numbers, but they're features that help represent the speech. That's called feature extraction. The next stage is we take all those floating point numbers, it might be samples of your waterfall or the spectrum of the speech or the pitch, and we convert it to a fixed number of bits, so we compress it to a known bit rate. We then do some FEC encoding where we add redundant bits to help protect it as it passes over the radio channel, but increases the bit rate. Then it will go to some sort of modulator, which converts that 1010 bit stream into an analog signal, which can be passed over a radio channel. On the receiver side, that analog signal is demodulated back to the bit stream. FEC decoding is applied and hopefully corrects some or all of the bits that were corrupted in its journey over the radio channel. Then there's a process we call dequantization, where those bits are converted back to the features or floating point numbers, and then we feed it into a speech synthesizer, which hopefully delivers reasonable output speech. Okay, so this is what's going on with RADE. We still keep the feature extraction stage, but now we replace a bunch of the other blocks we had before with the RADE encoder. It takes those features and directly generates QAM symbols, and I've got some examples of the symbols it generates that I'll show in another slide. We then pass it to a modulator, and the type of modulator we're employing is called OFDM, which is basically a bunch of parallel carriers. We split those symbols up into a bunch of parallel carriers. That goes over the radio channel. There's then an OFDM demodulator, which extracts the received QAM signals. That gets fed into the RADE decoder, which directly generates features that can be synthesized. Now, the speech synthesizer is a high-quality machine learning synthesizer, so it's much better than what we had before. So it gets quite high-quality speech from those features. Now, the blocks here, the RADE encoder, the RADE decoder, and the speech synthesizer are all built with modern machine learning techniques. The other blocks, OFDM, etc., are using classical DSP. So it's a bit of a mixture of the two technologies. So once I said, as an example of the sort of features that it extracts, is the sort of thing you see on your waterfall on a radio. It's just little slices of the speech spectrum. It turns out they're enough to synthesize high quality speech from. And once again, the encoder takes features and produces symbols we send over the channel. And the decoder takes symbols and produces features at the other end. The way we trained it is we used around 200 hours of speech, and we started with a blank encoder and decoder. And then as we put the speech through it, we simulated a channel corrupted by noise and a bunch of HF channel impairments. So the idea is that the whole network learns about how it can be corrupted and learns how to regenerate the features in a way that sounds good at the output. And then there's a classical DSP modem wrapped around all the machine language, mainly for synchronization purposes. The database includes multiple languages. The data set, that 205 hours, is from many languages and many different recording conditions and things. There's quite a few high-quality data sets available from the speech recognition community. So before we talked about the symbols being sent over the channel, QAM symbols, you've probably seen on the left a QPSK constellation. This kind of these diagrams represent both phase and amplitude. And in this case, QPSK is 4 dots. Each dot encodes 2 bits of information in a digital modem, or even in a classical digital voice over radio system. They're human designed, these constellations. There's good reasons behind them. But on the right is what comes out of RADE. It basically looks like noise to a human. So we haven't kind of worked out the structure itself, but that's what the constellation looks like. Because it's kind of two-dimensional, yeah, it wouldn't really represent them that way. Okay, so just to conclude, we've talked about how doing things with machine language is now about training and data sets and a little less about design than it used to be. RADE stands for Radio AutoEncoder. An autoencoder is a particular machine language kind of design that we've employed. RADE uses ML, machine learning, combined with classical DSP. It delivers high quality speech over HF for both low and high SNRs. You can run it with the FreeDV GUI application, a couple of sound cards and an SSB radio. The work's been kindly supported by a grant from the ARDC. And we used a bunch of crowdsourced testing last year, so thanks to many hams around the world. They're mentioned in the many blog posts that document the development. And this is all developed by hams for hams. So a few links. You can download the software from freedv.org. There's several sources for help. There's mailing lists. There's the QSO Finder chat, which I'll show you in a moment. There's Discord chat. QSO Finder is a way to find people to talk to and communicate. So I'll show you that. Get the browser up. Oh, there we go. So this runs for a few pages, but there's an opt-in option when you download the FreeDV GUI application for you to connect to this site. And there's a bunch of call signs there down the left. Locators and what frequency they're listening in for. There's a couple of people, I think, looks like they're transmitting down the bottom, the pink lines. So that sort of gives you some idea of where people are, where they're located, who's transmitting, who's not. There's also a chat window associated, so you can talk to people and coordinate a QSO online. There's some integration into PSK Reporter. So that's, I think, for the last 24 hours. Sorry, that font's a bit small for me. So yeah, there's a bit of activity going around in various places around the world. Very popular in Japan. And as I said, this is opt-in, so this is kind of like a sample. Not all of these people will be logging. Not everyone will be logging their presence on the system. So there's a fair bit going on down there in Japan. Yeah, there is a bit. And there's also, in parallel with this presentation, there's a RAID intro document that covers a lot of the same material spoken about tonight. So that's it for the presentation. Did we want to open it up for questions?
Have any questions from the floor? Okay, just bring the mic over.
Just a quick one that was prompted by what we saw on the QSO Finder. There was someone at the very bottom looked like they were transmitting on 10 gigahertz. Does it work just as well on the higher frequencies?
It'd be pretty sensitive to frequency offsets and things, so as long as you've got a good stable radio. Yeah, I didn't know there was any 10 gig work going on, so well spotted.
Is there someone on Zoom? Phil?
So I love the example of the ML detector, which is, well, the diode simulation by an ML detector. I wonder, David, did you actually listen to the output of that as well as the simulation results you showed?
I haven't, just pure simulation and plotting. I did, however, check the network by eye to make sure it matched something like a diode.
Okay. Can I ask another question?
Yes.
So with the ML weights, would it be useful to have different sets of weights for different channel conditions?
Yeah, generally the idea is you try to train something that'll work on a range of conditions because it's difficult to swap them in and out at runtime. But yeah, potentially. I have one of the challenges with ML is to train something so that it works on a range, so it's generalized. So this one was checked on a range of fading channels from AWGN channels right through to fairly fast fading, and did quite reasonable results. It's trained on a moderate fading channel as the sort of the baseline.
Anyone else? Grant.
Couple of questions. First of all, have you played at all with it with an interference limited channel or interference on the spectrum? Because I mean, HS usually far from clean.
Yes, we developed it with things like interfering carriers and co-channel interference. Made sure it didn't do anything too silly with that. It tends to reject them quite well. It also rejects impulse noise, which we didn't train for, but we were lucky.
How does it cope with radars?
As long as it's a few dB or two beneath the wanted signal, you're okay. Once you get above that, it gets a bit harder.
Okay, thank you.
Yeah, Simon, if I may, please. Yep. Does this system work? Can it be encrypted?
At the moment, no, because it's not digital, and to have a proper crypto, one that would pass all the required tests, would not be possible with this sort of thing.
Okay, thank you.
Yeah, I've got two questions, David. Comparison and advantages over, say, standard 3dV signal.
It's much, much better quality than regular, the previous 3dV modes. They've kind of gone away in terms of day-to-day use.
And the second one, how much compute does it really need to be effective?
It would run, once it's in an optimized C form, it would run something on like a Pi 4.
Okay.
You need a cell phone class processor, not a microcontroller.
Thank you.
Am I right that there's no feedback between the receiving loop machine learning and the transmitting machine learning?
No, they're trained together.
They're trained together, but when it's operational,
no, there's no other channel. No.
And so, and the bandwidth you're using is 2.6.
Over the RF bandwidth is around 1500 hertz. Right. The audio bandwidth is 8 kilohertz. Right.
Thanks for the presentation, Dave. Two questions. One, off-the amplifiers need to be ultralinear, as I understand it. So you've got I guess you can't get a lot of power out of this because of the wide dynamic range. Is that a true statement?
No, we've optimized this to have a very low peak to average power ratio of less than 1 dB. Okay. So you can just about run Class C.
Ah, okay.
And that's one of the reasons it works so much better. We've got 4 or 5 dB out of that on top of any other digital mode or indeed SSB.
Oh, okay. Yeah. So that was the other question on the VHF weak signal like sideband. How would you got a 4 dB figure in your demonstration? How far with it? You don't quite fading's different on VHF.
At about we sort of say minus 2 dB over that sort of channel.
How does that compare to just a normal 2-3 kilohertz channel? Can you hear it? Is it not?
It depends on the operator. There are some SSB guys who can pick stuff up at 0 dB SNR, especially flat fading, with no fading. So, but it's pretty rough. At about minus 2 dB, you're getting about a 30% word error rate. If you shout your call sign 5 times, you're going to get through. But it's not conversational.
Sure. But we're getting processing gain off the old analog. What we yes, thank you very much.
Last one, you're passing the output from the ML thing is CRAM symbols. Is there any opportunity that you could add extra symbols to add forward error correction on top of the ML learning, do you think?
It actually outperforms FEC in many ways. So it'd go backwards if you added FEC. And the symbols that are being sent are analog. They're continuously valued. They're discrete time, so we only update them X times a second, but they're continuously valued. So it's a bit hard to put FEC. It outperforms this conventional system where you had it FEC. FEC codes have certain properties where they break at certain bit error rates, and this operates well beneath that.
When we looked at your frequency diagram, looking at the discrete frequency diversity, that was quite a good, basically it looked like a noise figure. Is there any randomization that you're doing to the output to get maximum frequency diversity?
No, we just say this is how many carriers we've got, and we go and train it, and that's what it spits out. And you can, by changing the training parameters, you can make wide or narrow band signals if you want. This is kind of our first attempt at it, that we got that something works.
There's no deliberate randomization.
No.
But you're getting it.
Yes. Well, it's random to us.
Right.
But it does reconstruct quite high quality speech. So there's some structure in there. What it's doing is it's exploiting correlations that we can't pick up by our own analysis, and that we kind of know are in there mathematically, but are difficult to analyze.
Have any experiments been carried out at LF and VLF frequencies?
I'm not aware of any. You're welcome to try.
Golden opportunity. Anyone else in the back here? All good. Right.
I'm just curious, the FGM signal you are running, what's the symbol rate of the individual carriers?
50.
Okay, so it's really quite low. But how many carriers in the channel?
30.
Okay.
So the core encoder is around 2,000 symbols per second. But don't confuse that with bits per second or anything.
No, it's different. I get it.
And then there's about 1,000 bits per second for synchronization information, like pilot symbols, unique word, things like that. That's kind of an overhead.
Any other questions online? No, all good, thank you. Anyone else on the floor? Oh, Grant, one more question. Gold coin donation for each one.
Well, here's the big one. One of the things that I have to poke the Oceania DX contest community to think about is the fact this year's the 80th anniversary of that contest. Having just seen this, I'm half wondering, is this the first opportunity maybe to give it a walk around the block on a big scale?
Yeah, I'm not aware of anyone using it in a contest today.
It'll challenge it.
Yes.
All right. Wheels are turning. We might talk.
Food for thought. Okay. We all done with questions here on the floor? Okay, thank you very much. So, David, thank you very much for a very interesting talk. Much appreciated. Thank you.